Hello and welcome back to Poor Man's Electronics Bench. In this episode I am going to discuss measuring high resistance faults in values that most common multimeters won't measure due to design limitations. I am going to demonstrate using a function on a vintage piece of test gear which is capable of a quantitative measurement of a 50 gigaohm resistance. Then I will cover a common digital multimeter that you may have or be able to purchase new or used that can make the same measurements by using a built-in conductance measuring function. And as a bonus, I will show that some older DMMs are Easter egged, or also equipped with the same capability and may not be marked for it, but are just different model numbers of meters with the conductance function clearly marked. I hope you stay tuned and enjoy the content. Hello and welcome to the next episode of Poor Man's Electronics Bench. In this episode I am going to go over measuring conductance or high resistive values using a couple of devices you might have or might be able to get availability to or create for yourself. One of the things that you find out about working with most multimeters that you have is they only can measure up to a certain range of mega ohms of resistance, somewhere usually between 40 to 60 mega ohms, maybe 100 mega ohms at the top end of the range. You'll find that that might be more than you need in some instances, but in other instances, like measuring leakage of capacitors, it's not going into a high enough range in order to make that measurement for you. Now there is a chance that you might have access to some devices that, or you might actually have them in your possession, then you don't really know that they're capable of making these measurements because they're not clearly marked on the meter. I'll show you in one instance it's basically an Easter egg. I'm going to go over the first device. The first one is some of the older capacitor testers, the older vintage ones. This one I have in view now is a Sprague T06A capacitor tester, along with being able to test values on capacitors and power factor, which is kind of the first version of checking ESR on electrolytic capacitors. This meter is capable of measuring resistive faults out to 50 kilo mega ohms, or what would translate to 50 gigaohms. It has a function on it called insulation resistance. You can see the two buttons on the top there. The first it's marked for mega ohms, and the first button is marked as 10K, so it would be 10 kilo mega ohms or 10 gigaohms. Second button range is 50K or 50 kilo mega ohms or 50 gigaohms. So what I'm going to do is check and see if it's actually functional for that. This unit I purchased a while back on an eBay auction. It is basically 100% original. It's a revision 1, which means it has a jeweled indicator light with a 6-volt bulb off the heater. The revision 2s are practically identical except for having a neon lamp working off a line voltage. But in this case we have what we have, but this one is perfectly identical. The revision 1 and 2 are identical. If you can get either one, there's basically no difference to their functionality. The only difference is that the indicator light, and they're fairly, if you can get one in good working shape, which this one is, this one's dead stock too. I'm reluctant to do anything to it because it might go back up for resale, and I might look for something that's a little worse for wear to use as a daily driver if I need one. That being said, though, I got to get back to using this device to measure into the higher resistant ranges. I do have a board. If you've watched my Gigaohm capacitor resistance tester, I do have a board with some surface mount devices. I have two 10 gigaohm surface mounts on there and 4 1 gigs. and that would put us in the range of being able to measure things on this meter. Got to go over some calibration on it. There's some buttons to set this. There's a press your selection for your 10K or your 50K button, 50 kilo mega ohm button, and at this point I've got leads connected. I have capacitor lever in the discharge position, which means these leads are connected to a resistor and the internals are disconnected. You have to set the meter to a set point using the voltage knob, and the set insulation resistance button really doesn't do anything to the value. And on the meter itself, it's got, see on the far range of it, it's got a set value. The shadow you see is the shadow from this light here. If I cover this light up, you can see that the meter is right on the set position. Let me zoom back out here, and we're going to get into a position where we can check a couple of resistors I have on the board here. So I'm going to go with the 10 gigs first. I'm going to put my, I'm going to connect them first. One thing about this meter too is these measurements are done at a safe low voltage. This is nothing that's going to have any electric shock risk, unlike your leakage current test. So in this case, I've gone over to the test position, and my meter came down a little bit. It came down off of. I can go to the discharge and disconnect and reconnect. You can see that it is. That is open circuit, and coming down, it's coming down right on the 10 kilo ohm line. So on the 10 kilo ohm range, that is very accurate. So we're going to change to the 50 kilo ohm range here. I've got this discharge. I'm just going to press the 50 kilo ohm button. I'm going to recalibrate my set point, and going to go from discharge to and it's off just a little, but pretty close. It's not an exact quantitative function value, but it's pretty darn close. So that's, I do have some 1 meg resistors I can task with this as well. We can see how those come up. I'll try it in the 50 range. It's in discharge and it's still at the set point. I bring it down and comes fairly close to that 1 kilo mega ohm or 1 gig position there. We go back to the 10 kilo mega ohm full scale. At the set point, and that kicks down, and that is just barely inside the money for the 1 kilo mega ohm and the 10 kilo meg range. So it's a working functional device for being such a vintage piece of test equipment. To be able to measure that resistive range accurately is quite surprising. And there's one thing I'm going to go over with this also, just to show the fact that this is accomplished with basically safe voltages, as I have a DMM here. I'll try to get a little more space on the bench here. Set at DC volts. Try to keep it in range here. This has an internal resistance of 10, so it's going to take this meter down when I hook it up. So it's got a 10 meg impedance on the meter, but this is on the 10 kilo mega ohm setting. 1.34 DC volts. And everything in this meter is based on 60 cycles, so there's no high frequency in it. AC component on it is only 0.34 volts. So that's perfectly safe to touch without any problems. And we're going to go up to the 50 kilo mega ohm range. I'm going to just for validity's sake, going to get this back up to the set point. .0 DC volts with a little over a half volt AC component. It's slowly building up. It's probably going to build up to a volt AC, but it's interesting that the impedance on this meter is a lot lower on AC than it is DC. In fact, right now it's up to 50 kilos. It's basically going to go open circuit, which is surprising. So that's one device that you might have access to that you don't think about using that function for, but it can work very well on troubleshooting a capacitor that might be a problem. I can try to dig one up. In fact, here I've got some ceramics on hand. One of them is a known problem child. You just have to find them. Let me get right back to you here. Okay, I'm back. We got some discount bulk capacitors, and one of these is a problem child. They've got it marked. These are not high voltage discs, but they are. I measured them as leaky, I thought, but they seem to be okay. Here, this one, a noisy one. Okay, this one is a 0.47 plus 80 minus 20, a 12 volt rated capacitor. So this can measure a fault in these capacitors without a problem. So I'm going to go back. I'm going to discharge, go back to 10 kilo mega ohms, and I'm going to get on the set point. I'm not going to be that fussy about it though. This is a bad one, and I'll compare it to a good one. Normally a capacitor like this would take a minute to take a charge and would slowly level out and go to a higher value open circuit as it took the charge. This one's not doing that. So we're going to take another one, same batch. Lo and behold, it's got about the same results, but it's slowly going up. Curiosity, I'm going to reverse polarity on it. A little lower value in the other polarity. Let's get back to this one. This one's behaving about the same on the insulation resistance, but we're going to go to the function for measuring leakage current. In this case, I have to use the calibration button. It's a 12 volt. So I've got it my 0 to 60, my calibration voltage for 12 volts. Meter indicates 60 milliamps. That's a 0.6 milliamp full deflection, so that's about a 0.2. I'm going to go with a, should be a good one. That one's about open. There's, according to the rated voltage for the milliamps on this, there's no current flow at all. So this would test as a good capacitor. We're going to go back to this one, and you can see it does have current flow, and it also has some noise on it too because the meter is fluttering. And there's something that's curious about this capacitor as well, is that if you reverse polarity it behaves differently. These are all supposed to be non-polarized. Oops. It's about a 0.24 milliamps to 12 volts. It's a very large leakage for a ceramic, but it's a lot less than this polarity. This other capacitor is nothing at 12 volts, and it discharged reverse polarity and settled down to 12 volts.
Read the inscription.
Hold on a second. There we go. So these are just probably not the best items to test for higher resistance or conductance, because they don't, lower voltage capacitors like this probably will leak some at some point, but that one still measured out to be a troublemaker. There's another device some people might have. It's kind of, they might not even know that the function is in there. It's Fluke multimeters. There are a few of them. I'm going to get this clear off the bench here. There are a few Fluke multimeters that have, and also if you're willing to make a purchase on a new meter, Bryman's another one that has some models, the higher end models, that have the ability to measure conductance. And those, the Flukes and the Bryman's can measure all the way down. They measure conductance, and conductance is measured as an inverse of resistance, and it's a directly proportional mathematical formula. And what it does for you is it just, I don't know how or why these meters are set up to do it, but they do it. And we'll go over a Fluke. I've got a Fluke 83 5 here, and if you notice on the front of this meter there is absolutely no indication that it measures conductance. But what you do is, if you go to your ohm range, you have your yellow indication button. You see you've got megaohms here, you've got nanofarads, it goes to capacitance. That's the range button. Okay. Press the range button a few times when you're in ohms, and all of a sudden you see a small letter N, and a large letter S, and you are now in the world of nanosiemens. And it's fun stuff because there's a quick mention of it in the manual, but it's not really something that is marked on the meter. Most people don't even know that that function is on this meter. And mathematically, what the minimum value that can be displayed on this meter, which is a 0.01 nanosiemens, works out to 100 gigaohms of resistance. So in this case, I am going to try to reposition the light here so it's not as shiny right on the meter. I'm going to relative this out as well as I can. Pretty jumpy. So going back to the connections on our board here with these 10 gig resistors, since the open circuit lowest value, that 0.01 is 100 gig, we will be expecting a 0.1 nanosiemens when we connect to that. And if we connect, let it settle down, it's coming up as a 0.12, so it's a little, it's saying that resistive value, well, I'll tell you, it's also, not sure if I've got the best connections on here. It's right around at 0.1, 1.12 to 10 gig. And if you go dead short, it's going to go display overload. I've got my other 10 gig resistor here. About the same thing. It is very, just I'm not sure if it's hand capacitance or anything from around there. And we're going to go to a 1 gig. That one should display a value of close to 1.0. That's a 0.59596. And remember, these are ranges that will clearly tell you whether a capacitor has any type of fault in it. I'll go back to one of these ceramics. That one's at too high of a short value. Let me grab another. I've got some. I've got some film caps. So 0.68 micro at 100. These should have very little to no leakage on them. See, it was an open circuit for a while now. It's actually charging up the capacitor with the voltage that's on those leads. I don't know what voltage it is, but it's less than, got to be less than 9 volts. So that's coming down, telling us that that's going open circuit just about to at least 1 gig. And the nice part about it is this is all done safely with low voltage. You can touch it, you can put your tongue on it. Let's try a different ceramic. I've got some picofarad range ceramics as well. Here we go. I got some 30 picos at 100 volts. Oh, come on. Trying to pull them out of the glue on those by the leads, or by the... And that one doesn't recognize any type of electrical conductance in it, and zeroed out the meter. Now this should be interesting, because this will give a value until it discharges and recharges. Very slight one. But there it is. So that's internally got leakage of 100 gigaohms, which is about all you can ask for a common low value ceramic capacitor of the picofarad range. So it's funny that this turns out to be an Easter, pretty much almost an Easter egg in this meter. It's disclosed in the manual. And now for the fun part. The meter next to it is an older model Fluke. And I don't know all the model numbers off the top of my head, but there is a range of these meters that is marked on the front of them for measuring conductance. I'm going to go into a quick gear change here and insert this. I was going to cover the information for these other older Fluke DMMs that I found online. I was just surfing around looking for meters to possibly use, and found a couple auction site meters. This is a Fluke model 8012A digital multimeter. Now this one has kind of clear markings on it for the fact that it has volts, kiloohms, and S for Siemens. And if you look carefully, there's function buttons that you push in pairs. The lowest two function buttons for your ohms, your microamps, and your volts, if you push them in simultaneously, would give you full range values displayed up to 2 millisiemens. The next two buttons are marked as 20 microsiemens, and the last two buttons would be a full range indication of 200 nanosiemens. So I'm not sure if there's a decimal point built into this meter. There may or may not be. So this is an example of a benchtop DMM that has this clearly marked. And then if we go to some handhelds, we have a model 8060A true RMS multimeter. And this one here is, if you look, it's got a Siemens function here with, you have to press the bottom button in, have the top button out, and then you press these two buttons on the top to give you a 200 nanosiemens full range display, or 2000 nanosiemens, I'm sorry. And then there's a third model meter. Whoops. Let me get back to my view here. This one is a 8024B multimeter. This one just indicates the one bottom button to be pushed in for the Siemens position, and then two of the top buttons pushed in for a 200 nanosiemens full range display on the meter. And just going back to the meter that I have, back to the video, and I was kind of wondering if that function just was built into the meter but wasn't marked. And in the case of this one, it's not. If you can clearly see, there's no marking or indication whatsoever that it is capable of doing conductance. Let me Let me turn this on and check just to make sure my leads are making a good contact here. I want to go 200 ohm range. Okay, we have a good contact inside the leads here. So the one thing I noticed about the meters that do measure and display conductance is the position of the buttons. They have the same fields of buttons. The only difference is this isn't marked for conductance, the other one is. But also those other meters, I don't know if they have a current measuring function to them. But the one thing about the button positions I was wondering is, like, there's some electronics where you'll find that there's functions built into them that might be in one model that aren't in another, but they might be in the other model too. They're just not marked or marketed because they didn't want to go through the extra display or let people know that, hey, these meters all do the same thing and we can market a totally different meter, which is kind of nonsense. Could have done it all in one. But in order to set it into the conductance range, all you do is you push the two top buttons together. And if you notice, in this case, it goes to an overload. If you disconnect the meters, it slowly goes down to a 0. Does that remind you of anything? It's behaving exactly like the Fluke 83 with that function. So in this case, we're going to go over and connect back up to one of our 10 gig resistors again. Remember, in nanosiemens, the 10 gig displays as a 0.1. So there we are, we're connected. Now granted, we don't have the resolution below that one, but look what we got. We have a 0.1. The 1 gig will measure out in conductance to 1 nanosiemens. So we're going to hook up to one of the 1 gig SMDs, and sure enough, it measures out to just under 1 nanosiemen. So there are benchtop models of the older Flukes and the handhelds, and if you have one of these older handhelds, this one in particular is a model 8021B, you might find the surprise of having a meter capable of doing conductance reading or high resistance values that you don't know you even had. So might be a good thing to go take a look at your meters, do a little research on them, and you can open yourself up to a world of measuring very high resistance in items without having to go out and buy any other test equipment or subject that equipment to high voltages, because in either one of these three cases, as you've seen, all of these devices work with less than a 10 volt potential, so it's totally safe. Unless there's some sort of errant static discharge built up on something, it's not going to harm or short out anything, and it's just a little thing that you can play with later on. So that's about it for this video. I thank you for tuning in and watching, and I hope you enjoyed the content and learned something from it. And feel free to like or subscribe in return for my next video when I make it available. Thank you.